Welcome back, everybody. High Tech Lab here. Today I want to be giving some closing remarks on why I switched from these lead acid batteries over to these new lithium iron phosphate batteries right here on the floor. One of the things I want to show for the record is the specific gravity, and I have here this Easy Red battery hydrometer. And one thing I want to mention is the gravities of this battery, and this is typical failure mode of most of these cells. If you look, this one is showing as good. It's got a bit over 1275 on this gauge. And I'm going to jump over here for video's sake. And you can see, still showing good on this gauge. On this cell, we're showing good, 1275. And now this meter is not temperature compensated, but you'll see why that doesn't matter here in a second. This is showing 1265. And this cell, 1275. So this is showing as a good battery. But we come over to this last cell, and I went in the order I went intentionally. You'll see this one's only showing as fair, pretty low gravity on this one. And this one's not as bad as some of the other cells, but I call this the 10.5 volt failure, because what's actually happening is one cell, in this case this cell right here, goes bad, and there's no way to individually recharge that cell. The only way to recharge it is to equalize the whole battery. And with these 8D batteries, I've not had any luck trying to overcharge or equalize charge them in order to rejuvenate a cell. So with my multimeter right here, I'm going to go ahead and probe the battery, red to positive and black to negative. And you'll see on the meter 10.68 volts. Now some of these ones that have truly failed are at 10.5 volts, but I'm going to go ahead and grab my clamp-on battery meter. Now I have this meter clamped on to the battery, and this is not connected to the rest of the system. You can see it's isolated, and I'm at a voltage measurement that matches where I was at before. Now this meter has a coil in the back, so it actually puts a load of 135 amps on the battery when I hit this button. So we're going to go ahead and put a load on it and see what happens. As you can see, it's dropped down to, I know this is not focusing very well, but we're at 9 volts, and this is starting to heat up a little bit. And if we look in these cells, not much is happening. So still holding the button, we're sitting at 9 volts. This cell is actually too low to be in parallel with other cells on this bank. So what happens is, when I have these parallel racks, right? So this rack is all in series, paralleled with this rack. All 4 of these are in series. This rack is paralleled with this rack. What happens is, since there's a weak cell here, this may be at a higher voltage than this shelf, and this shelf will push power into this battery and turn it into heat. And as soon as I remove this battery because it's bad, immediately another cell in another parallel string has the ability to go bad and drag the system down. So that was the biggest problem using these lead acid batteries, was there's so many in parallel and so many cells that it just was not easy to keep track of what was failing. Another thing is, each battery has 6 cells. So right now, these are part of the good ones left. There's only 7 good batteries. I believe it's 4 of these on this shelf, 2 down here, maybe that one, and I think that one. But I only have 7 good batteries left out of these 12, and that's 7 good batteries left out of all 32 that I had on both racks. And if you look, this one we just tested, it may be a little hard to see, but it's scratched out for February of 2018. So this battery really didn't get much life out of it, and that's really unfortunate, because these batteries cost me $200 a piece. Now the side of the warranty comes in when these don't last so long, because this has been sitting for approximately 2 months. I went through all these batteries on April 20th and checked the gravity in all of them, the charge, and this one actually used to have the Sharpie mark saying that it was okay. You can see kind of where I erased it in the dust. But now here we are, this battery is no good. So since 420, I upgraded to my lithium, stopped using this battery, and now that it's rested, we've had a chance to see that it's failed. And if I grab my meter, and I go to another one that was taken out of service at the same time, you can see 12.79 volts. If I go to the next one that I know is okay, 12.81 volts. So they're still good batteries, a couple of them, but all in all, multiple of them had failed, and that's why I'm completely going away from the lead acid. The cool part about these prismatic cells is if one cell is not happy, not only will these balance leads equalize it out, but I can also replace individual cells if they go bad. Now, it's typically good practice to replace all the cells together. However, if you have a newer bank and one cell fails, you're not going to go replace the whole bank if there's a manufacturing defect. But all in all, you end up with a much cheaper cost to repair throwing away one of these versus one of those 6-cell batteries there. Let's talk another reason why I'm getting rid of these batteries. These 12 batteries right here take up a lot of space. And like I said, some of the cells were failing, but that 100 amp hour prismatic lithium iron phosphate bank right there is double the performance of these batteries right here. These batteries will last thousands and thousands of cycles versus these batteries that have only lasted a couple hundred cycles. I'd estimate about 500 cycles I got out of these before I started having problems. So you can see the cost of that versus the cost of this per year. This is actually far more expensive, even though it was a lot easier to get started with these lead acid cells. So the point I'm trying to make is even though there's a bigger upfront cost with lithium iron phosphate, the return over the years that you're not having to buy new batteries are where you're really going to save your money. And I recommend to anybody going off grid, go with the lithium iron phosphate. And I say that because I've tried the lead acid. I've had my struggles with the lead acid, and it's really, you don't get the performance. They take a lot of space. They waste energy. They self-discharge. They generate heat, and I need to install ventilation in order to get the gases that they produce out of the room. With the lithium iron phosphate, no ventilation is needed. I can actually run this AC unit right here, which is running right now. That's what some of the fan noise is, and keep the room cool because I don't actually need to remove air from the room and pull in a bunch of hot outside air. All in all, I'm looking at removing this whole shelf from here and just leaving 4 batteries as a backup so I can jump over with the fuse like I had talked about. That's kind of the closing of ditching the lead acid, moving to the lithium ions or lithium iron phosphate to be more technical. So if you guys learned something in this video, be sure to leave a thumbs up. If you haven't already, hit the subscribe button, turn the bell icon on so you can get notifications whenever I upload a new video. I'll see you guys in the next one. And again, if you have any questions at all or my math didn't quite add up, comment below. But yeah, I'll see you guys in the next video. See you later. Bye.